All praises are due to Allah, the cherisher and sustainer of the worlds. You're watching Adorhythms Biology, and I'm your friend and host, Dr. Zubair Shanib. Today, we're going to take a third part of the enzyme, that is enzyme inhibition. So far, we have studied the overview in the part 1 and then enzyme kinetics in part 2, and now today we will talk about enzyme inhibition. Before I begin, let me give you an idea why enzyme inhibition is worth of studying. Number one is, when you talk about enzyme inhibition, you always understand that the first question that arises is, why do we need to inhibit enzymes when they are biological catalysts? Why are we in need of inhibiting them? Or why do they inhibit? Important thing is, you have to understand that we never wish to inhibit our enzymes. But when you are studying enzymes in vitro and you are studying the mechanism of action, that's one reason you want to inhibit them, to see how the substrate fits into the active site. That's the reason number one. The reason number two is, when we are looking for new drugs that can target cancer, drugs that can target infectious disease causing microorganisms. So at that times we think of enzyme inhibition. So today, when we talk of inhibition in case of enzyme kinetics, looking it from the prism of enzyme kinetics, we will see that enzyme inhibition is divided into two main categories. One category is reversible, and another category is irreversible. So let us think about these two first. What is a reversible reaction and what is irreversible reaction, or what is inhibition in case of reversible and irreversible? See, if something binds to your enzymes very tightly with a covalent bond, in that case you call it as irreversible inhibitor. But as I talked in the early examples, if something binds to an enzyme for a brief period of time through a non-covalent bond, we call those interactions as reversible interactions or reversible inhibition in this case of the study. So before I venture into the reversible phase, let me first briefly tell you about the irreversible. I will give you a few examples. For example, there is a nerve gas called as DIPF. The full form is diisopropyl phosphofluoridate. It's a component of a nerve gas. You might have heard about the nerve gas tragedy in Syria. So what it does is, it binds to one of the important receptors that is involved in neurotransmitter. So what you see is, in the postsynaptic cell, there is a receptor called as acetylcholine esterase. So what does it do? The acetylcholine esterase, it converts the acetylcholine back into the acetyl group and the choline part. Fine? So it is a receptor in the postsynaptic cell. So what DIPF does is, it binds to the receptor of acetylcholine esterase and prevents it from doing so. So when there is no action potential, the person can die because of the respiratory failure, because there is no command coming to our respiratory system, or you can say your breathing system, to inhale or exhale. Another example of irreversible inhibition is iodoacetate. This compound was used to study whether the active site was having any thiosulfate bond. So iodoacetate, what it does is, it prevents the formation of the thioester bond. As such, you understand that this enzyme has a thioester bond at its active site. Fine? So that is why we use inhibitors, to study them. Okay. So these are the two basic examples of irreversible inhibition. Now let us come back to the reversible inhibition, in which we will be talking about them in much more detail. So let us now take the example of reversible inhibition. So when you talk of reversible inhibition, reversible inhibition, so what does the term tell you? The term tells you that this inhibition is only for a brief period of time. That's why we call it as reversible. The second thing reversible tells us is that once the inhibitor binds to the enzyme's active site, with time it can go back and the substrate can again bind to the enzyme. It means the enzyme will work again. So until the inhibitor is there, enzyme inhibitor is activated. But when it is back, then it will again start functioning. That is not the case with irreversible inhibition because they bind to the active site by covalent bond. Here, in case of reversible inhibition, they bind with non-covalent bonds. For example, hydrogen bonds. For example, hydrophobic bonds. For example, weak ionic interactions. Fine. Now we have divided this reversible inhibition in three different components. Okay. First is competitive inhibition. Competitive inhibition. Second is uncompetitive inhibition. Fine. And the third is mixed inhibition. Mixed inhibition. So we have a competitive inhibition, we have uncompetitive inhibition, we have mixed inhibition, which is also called as non-covalent inhibition. Sorry, non-competitive inhibition. Fine. So we divide them into three categories. Now let us understand from the terminology what they mean. From the terminology, it seems that the competitive inhibition, in this case, this inhibitor is very similar in structure to your substrate. That's why it has the ability to bind at the active site. So this is competitive inhibition. The inhibitor is very similar to that of the substrate and it binds at the active site. Another example of irreversible inhibition is uncompetitive inhibition. So the word itself says uncompetitive. There is no competition between the substrate and the inhibitor, but then still it inhibits. How does it do it? It does it by binding to a site other than the active site. And in that case, what it does is it binds to the enzyme, changes its active site because of the change in the morphology of the active site. Fine. Now we have mixed kind of inhibition. So what is mixed inhibition? Again, when you talk of mixed inhibition, it means once we understand these two, I will tell you what the mixed inhibition is all about. So let us first take the example of the competitive inhibitor. So it seems mixed is a mixture of these two inhibitions. Okay. Let us see now with examples. And one of the important things you have to remember here is that you will be asked about in the exams is what happens to the Km and what happens to the Vmax. That is what they ask you in the exam. And at the same way, they will ask you how you can plot these changes in the Michaelis-Menten equation, that is the hyperbola graph, and what happens into the Lineweaver-Burk plot. Fine. So they will ask you this thing. Fine. So when you talk about these two things, when you talk about now enzyme inhibition, understand that whenever an enzyme is inhibited, its ability or its efficiency is going to decrease. And its efficiency is determined by its Vmax or initial velocity. So always remember, whenever there is inhibition, you will always find it that the enzyme Vmax is never going to rise. It has only two ways. Either it remains constant, fine, or it goes down. Always remember, in any case of inhibition, Vmax never increases. Whereas in case of Km, in any of the three cases, it may either go up, or it may go down, or it may remain constant. Fine. So remember that in every inhibition, Vmax never goes up. In one case, that's competitive inhibitor, it remains the same. In other cases, that is uncompetitive and mixed, that is non-competitive, it always decreases. You understand that, it's very logical. Now let us start first with the competitive inhibition. So when you talk about competitive inhibitor, in previous lectures, I have given you an idea of enzyme, as Fisher gave us the idea, that enzyme acts as a lock and the substrate acts like a key. So let us take this example in case of competitive inhibitor. Competitive inhibition. Okay. So let us say that this is your enzyme, fine. It has the ability to bind to its substrate, good. Then it makes an enzyme substrate complex. Then it further goes down and forms enzyme product complex. And finally you get enzyme out and then the product out. So you remember in the last lectures, this enzyme is recycled back here so that it can again bind to the substrate. But what happens now? Look at what happens now. In the presence of enzyme, in the presence of the inhibitor, this enzyme binds to an inhibitor, okay, and it forms something called as enzyme inhibitor complex. So in this case, what you are looking here is the enzyme binds to an inhibitor, forms an enzyme inhibitor complex, and there will be no reaction at all. No reaction. Fine. So now they will ask us, what happens to Vmax? What happens to Km? How can you represent it in Michaelis-Menten equation? How can you represent it in line-Weaver-Burke plot? Abhi, let's see that. तो अगर आपने पिछला लेक्चर आपने अटेंड किया हो तो मैंने आपको एक अच्छी सी फॉर्मूला दी थी जिससे आप निकाल सकते थे कि what is happening to the Km and Vmax in the cases of the normal reaction. So let me draw it here for you. Okay. So I told that enzyme efficiency is directly proportional, your Vmax is directly proportional to your enzyme efficiency. Okay. Enzyme efficiency is inversely proportional to the Michaelis-Menten constant. I have defined it very briefly in the previous lectures. Those of the students who have not understood Km, please go to my previous lecture. And then this Km is inversely proportional to the affinity. कल का लेक्चर है affinity of किस चीज़ की? Active site for its substrate. तो आप क्या देख रहे हैं इस यहाँ पर रिएक्शन जो अभी मैंने दिखाई थी competitive inhibitor में, enzyme then binds to the inhibitor or it can bind to the substrate. Here it can form enzyme substrate complex, but in this case it forms enzyme inhibitor complex and no reaction takes place. Fine. Okay. Now let us look at this. So एक बार आपका enzyme inhibitor bind हो गया, so what happens to the affinity of an active site for a substrate? It decreases because now there is a competitive inhibitor. Km increases, enzyme efficiency is decreased because inversely proportional, so does the Vmax. So Vmax should also decrease. As I told in the beginning, Vmax can either remain constant or it will always decrease. Now, because it's a competitive inhibition, there is always a competition between a substrate and an inhibitor. Okay. I have discussed to you last time that if you consider this lock and key theory, Fisher's theory, this is your enzyme and this is your original key. Now this is your competitive inhibitor, it's a duplicate key. Or it's very similar but it's duplicate. So what does it do? If you have more number of inhibitors, this is an inhibitor, This is a substrate. Both of them look very similar in their structural things, right? Every book tells you that. But what I am telling you is that if the inhibitor goes inside the active site, fine, it becomes enzyme inhibitor complex and it doesn't allow the reaction to take place. Now look at this. If you increase the concentration of the substrates in a solution, it will compete with the inhibitor. So once the inhibitor goes in, the key gets jammed in the lock. The duplicate key gets jammed in the lock, so the original key cannot go in. So what happens is affinity of the substrate for the active site goes down, Km increases, efficiency decreases, and Vmax should also decrease. But there is a thing called as substrate concentration. In competitive inhibitor now, if you increase the concentration of your substrate, it will outcompete the inhibitor. So increasing the substrate concentration makes the Vmax stable. So Vmax remains the same. In case of competitive inhibition, it doesn't go down. Why? Because when you increase the substrate concentration, now the substrate will bind to the enzyme, throwing out the inhibitor. Okay. Now what happens? How is it reflected in the Michaelis-Menten equation? So let us understand how is it reflected in the Michaelis-Menten equation. So the Michaelis-Menten equation tells us that the initial velocity is can be equal to maximum velocity depending upon what's happening with the substrate concentration divided by Michaelis-Menten equation, plus sign is here and again substrate concentration. So in case of competitive inhibition, this equation changes, it becomes alpha Km because alpha is increasing here as I showed you just now. So there is an extra weight on Km, that is alpha, so Km increases. When Km increases, efficiency of enzymes goes down, so velocity should also go down, but it doesn't go down because when you increase the substrate concentration, it outcompetes your inhibitor. And in case of Lineweaver-Burke plot, if you write it like this, 1 by V0 is equal to 1 by Vmax plus Km by Vmax into 1 by substrate concentration. So here you can see that the Km increases by a constant of alpha. Alpha comes here. Now let us see how is it reflected in the graphical form. Okay, so let us see that. Okay, so let us first make a hyperbolic graph, and at the side by side we'll make a Lineweaver-Burke double reciprocal plot. So let us first make a hyperbolic plot. So it is like this. Okay, there is a straight line, goes like this. We always plot substrate on the x-axis and initial velocity on the y-axis because it's a dependent entity. So this is an independent entity. This is an independent entity. We plot it on x-axis. Dependent entity, we plot it on y-axis. This is Vmax. Go to my previous lecture if you forgot about it. Okay, and this is your Km. Km is the substrate concentration where velocity is half that of Vmax. Initial velocity reaches half that of Vmax. So when there is a competitive inhibitor present, what is happening is, in case of competitive inhibitor, what happens is it goes down. So Vmax goes down. Fine. You can see now this is a saturation point, this is Vmax, and now in case of competitive inhibitor, you will find that although now the Km is increasing, the Km of this comes here. So the Km increases by a factor of alpha. So when Km is increasing, you can see that it becomes very difficult for an enzyme to go to the maximum velocity. Let us see what is happening on the Lineweaver-Burke plot. So again, we have a Lineweaver-Burke plot like this. Okay, Then we have a straight line like this. At this point we have something called as 1 divided by Km. In negative is the mark. Here we have this as 1 by Vmax. Okay, fine. And this is 1 by substrate concentration. We are plotting always the graph between substrate concentration and initial velocity. So this is 1 by V0 initial velocity. Okay. Now let me put something in your mind and it will make your life very easy. Number one is, what you do here is you start to make it 0 in the center. Okay. Let us say this is 0. Okay. And this is -2. And this is -4. In this case, this is 2, this is 4. Okay, on the right hand side it's 2 and this is 4. Fine, done with it. Let us see what happens in the what happens to the Km in case of the competitive inhibitor. How will we reflect it on the graph? So I said that Km is increasing, so -4 and -2. -2 is greater than -4. So if Km is increasing, it shifts here, but you will see that the y-axis remains constant. So the graph looks like this. Fine. So what you are saying is the slope of the reaction. So this is so you will find that there is no change in the interception on the y-axis, but you have seen that Km shifts from -4 to -2 in case of the competitive inhibitor, as we have already described that Km increases. Now what happens to the what happens to the initial velocity, or you can say that what happens to the 1 by Vmax? So what happens here is it remains constant because all of the two lines are going through the same intersection. We already discussed about it. Okay. Now let us take an examples of a competitive inhibitor. Before I venture into the uncompetitive and non-competitive or mixed inhibitor, I will give you a few examples of a competitive inhibitor. So you might have heard about a reaction in the Krebs cycle. So the best example I can give of competitive inhibitor is that we have a succinate. It's a reaction of a Krebs cycle where succinate is converted to fumarate and we get something called as FAD. FAD is getting reduced and it is forming something called as FADH2. What happens if you add malonate to it? So malonate, it works like this. So if this is original key, okay, the original key is succinate. This is your succinate dehydrogenase enzyme, fine. And now here is an inhibitor, is a malonate. So what it does is the malonate comes and it gets into the active site and gets jammed inside. So a key, it gets jammed in the enzyme itself. And which key is this? It's a duplicate key, that is the malonate. Another good example of competitive inhibitor is methotrexate. Okay, methotrexate is used as an anti-cancer drug. Fine. So methotrexate, what it does is we have a reaction in case of humans that it does is if you have to make a folic acid, which is a very important component of your nucleotides. Okay, so we have dihydrofolate. We start with PABA, that is para-aminobenzoic acid. It is being converted into dihydrofolate. Dihydrofolate is further converted to trihydrofolate. Okay, and this trihydrofolate forms something as folic acid. Okay, and it also becomes a very important precursor in nucleotide biosynthesis in forming deoxythymidine monophosphate. So the enzyme here from dihydrofolate to tetrahydrofolate, the name of the enzyme is called as the name of the enzyme here we have this inhibitor that is called as methotrexate. Methotrexate. So the enzyme name is tetrahydrofolate synthase. Tetrahydrofolate synthase. So what you find here is the methotrexate acts as a competitive inhibitor for dihydrofolate. So dihydrofolate is an original key Methotrexate is a duplicate key, and methotrexate binds to the enzyme active site and jams the active site, so no substrate can bind in. Okay, so these are the two best examples which I have given for the competitive inhibition. Now let us talk about the uncompetitive inhibition. Okay, just I will add one term here, that is UN, an uncle. Uncompetitive inhibition, an uncle inhibition, just to make you understand or remember, it's just a mathematics. Uncompetitive inhibition. So watch closely what happens. Okay, so if I tell you that this is your active site, this is your enzyme with an active site, and this is your key, the original key that has to fit in the active site. This is the original one. Okay, so what happens in uncompetitive inhibition? The word itself says uncompetitive. There is no competition between the substrate and the inhibitor. Good. So what happens is the original key, in this case the original key binds to its enzyme and forms an enzyme substrate complex. Okay, inhibitor is nowhere in the site, so the key is inside. Okay, now watch here closely. This is an enzyme, this is a substrate, this is your enzyme substrate complex. So what happens is in uncompetitive inhibition, the presence of the inhibitor. So what is the inhibitor here now? The inhibitor is like this. So it's a U-shaped magnet. Consider the inhibitor as a U-shaped magnet. It binds to the enzyme at a site other than the active site. Fine, it doesn't bind to the active site. It binds at a site other than the active site. So consider it is a U-shaped magnet or horseshoe-shaped magnet. Fine. So what it does is, your original key is inside, it jams the original key itself because of the presence of the inhibitor, and the inhibitor binds at a site other than the active site. So what happens is, in case of the reaction, I will make you understand here what happens in case of the reaction is, you have first an enzyme. Fine, it can bind to a substrate like this. It can form an enzyme substrate complex, which can finally lead to the production of free enzyme and the substrate and the product. So this enzyme can be reused, but what happens here is, the inhibitor doesn't bind to the enzyme initially, but once the enzyme substrate complex is formed, then only it binds. So here it changes a reaction into enzyme substrate inhibitor complex. So what is happening? The original substrate is binding, no problem initially. It's forming enzyme substrate complex. But once the enzyme substrate complex is formed, then the inhibitor comes in. Then the inhibitor comes in and makes something called as enzyme substrate inhibitor. And now let us see what happens to the Km and Vmax. So understand that there is no change. There is no change in the binding of the substrate to the enzyme. So you can say that if you use the formula, so Km remains. So Km goes down and your Vmax also goes down. As I told in the beginning, Vmax always goes down or remains constant. It never increases. Only thing you have to remember about what is happening to the Km. So if you take this formula now, which I have provided you in the beginning, that formula was like this. So what we have is, we have something called as Vmax. Depends upon how efficient the enzyme is. This is inversely proportional to your Km, and Km is inversely proportional to the affinity of active site. So let us see what is happening here. There is no change, or you can say the enzyme, the affinity of an enzyme's active site for its substrate increases. Why? The inhibitor forces the enzyme and the substrate to bind to each other. If it forces, it means it's increasing the affinity of the substrate for its active site. So you can here say the affinity increases So Km decreases, so efficiency of the enzyme should increase, because for every efficient enzyme the Km value should be as low as possible. So because it's decreasing, enzyme efficiency is increasing, so you can say the velocity Vmax should also increase. But what is happening is it is getting decreased. So what is the reason for this decrease? The reason is once the enzyme substrate inhibitor forms, there is no reaction further and no products are formed. That is why Km also decreases. But if you consider this formula, it should increase. But then use your mind and see that Vmax never increases, as I told you in the beginning. So it decreases instead. So in uncompetitive inhibition, both Km and Vmax decreases. Now let us see how we plot them on the graph. Here I will use only one graph, that is Lineweaver-Burke plot, and see what is happening in this case. What is happening and where is the location of the Km and Vmax. So here is our Lineweaver-Burke plot. Okay, so this is our normal reaction. This is minus 1 by Km. Okay, here we have 1 by Vmax. Plot always starts with the substrate. Here it is 1 by V initial velocity. Fine. Okay, so now this is a position of an Lineweaver-Burke plot when there is no inhibitor present. So once the uncompetitive inhibitor comes, what is happening to the graph? So graph is, so I told you Km is decreasing, so let us make it as 0. This Km is minus, say, 6. This is minus 4. Okay, and here it is 1, 2, oh sorry, it's 4, 6. Here it is 4 plus 4 plus 6. Okay, so let us see what happens to the Km. So Km is decreasing. Km is decreasing means it is going more negative, towards the negative. So if we plot like this, it's a minus 6 here. Okay, it's more negative. So now Km is decreasing means more towards the negative. So graph will be like this. It will start from this and it will be like this. So in case of uncompetitive inhibitor, you will find that Vmax also decreases. Fine, Vmax also decreases. So when it decreases, here I will say it goes from 4 to the higher value. Say this is a 5, value number 5. Here plus 5. So I said Vm decreases. Always remember that it's an inverse relationship. It is 1 by V0. Fine. So if V0 is going down, or say if Vmax is going down, I will write Vmax. So we say that in case of uncompetitive inhibitor, Km is also decreasing and Vmax is also decreasing. So what is happening here then? So if I say this is decreasing, so from original value it is 4, it is decreasing, it is becoming 5. So 5 is in the denominator. What does it mean? It means if it is initially at the 4, so 1 by 4 is 0.25. And what is 1 by 5? Let us do it. 5 2s is 10. So it's 2. See, the Vmax is decreasing. So initially it was 4, so 1 by 4. Now it's 5, it's 1 by 5. So 1 by 4 is 0.25 and 1 by 5 means 0.0. 5 2s is 10, 0.2. So you will see it's 0.2. So Vmax is decreasing. आप यहाँ देखिए, it's 0.25 and then it's 0.2. So Vmax is decreasing because of an inverse relationship. Fine. So this is a case in case of uncompetitive inhibition, where what happens is Km also goes down, Vmax also goes down. And when you represent Km, more down means towards the more negative, so it moves from this place to this place. And in case of Vmax, it also goes down. So because it's an inverse relationship 1 by Vmax, first if it is normal is 1 by 4, so it's 0.25 comes the value. And when it's when it's decreasing, the value is 1 by 5, so 1 by 5 is 0.2 and 0.2 is lesser than 0.25, fine. So this is a case of what happens to the Km and Vmax in case of uncompetitive inhibitor. Now let us take the example of mixed inhibitors. That's the last part of the study. What is happening to the mixed inhibitors in mixed inhibition? So in this case we call the mixed inhibition is also called as non-competitive inhibition. So let us now say that we have the normal reaction here, that is the enzyme combines with the substrate, it forms the enzyme substrate complex, and then it leads to the formation of enzymes plus product. Okay, so let us take the example of key and lock again here. Now in case of non-competitive or mixed inhibition, the inhibitor can bind at two different places. It can bind like here, it can bind to, inhibitor can bind here also, and it will form enzyme inhibitor complex. Okay, and inhibitor can bind also after the enzyme substrate formation is done. So inhibitor comes in, it forms enzyme substrate inhibitor. So in both the cases, the reaction, there will be either no reaction here, and at the same time in this case also there will be no reaction here. No matter how much substrate you increase now, it doesn't make any difference. In case of uncompetitive also it will not make any difference. In case of competitive also, in case of non-competitive also, it will not make any difference. So this is what is happening. So let me talk the same theory in the case of lock and key theory. So again you have a lock as an enzyme. Okay, it is an active site. Again the key is original key. It goes in, and now here a magnet binds to it. That's a site other than the active site, and because of the binding it alters the, it makes some conformational changes. So once the original key is in, it is locked inside again. So again you have jamming of original key, jamming of original key, jamming of original key. Let me take you back. In case of competitive inhibitor, we have a jamming of the duplicate key. In case of uncompetitive inhibitor, it is the jamming of the normal key because of the presence of the U-shaped magnet, and always after the substrate has bound to the enzyme, not before that. In case of mixed inhibition, it can bind before the reaction, it can bind after the reaction. So again it's a jamming of the original key if it is at this place, and this one we have already studied. This comes in the form of uncompetitive inhibition. Now we call this as a mixed inhibition, and now we'll be only talking about this case, and we can rename it as non-competitive inhibition. So best example of this non-competitive, let me continue this with an example. Okay, so let us see what is the example of this non-competitive inhibition. So what happens basically is the key is original, the lock enzyme binds to the original key, but before it's about to bind, the magnet has already bound to it. Okay, so let us give an example of a non-competitive inhibitor. The example is, you might have seen in a calf stomach we have an enzyme called as renin. And what's the job of the enzyme renin? So renin, what it does is converts your lactose, which is a disaccharide, into glucose and galactose. But there is a non-competitive inhibitor called as pepstatin. Pepstatin. So what does this pepstatin do? So if we say that this is our log, okay, the enzyme, that is its active site here. Active site is right over here. The key is original, no doubt about that. That's the substrate. This is enzyme and this is the substrate. It binds, before it binds to it, an inhibitor has already bound to an enzyme. So what happens is once the original key is inside, it gets locked up. Fine. Why it gets locked up? Because the inhibitor binds at a site other than the active site. Okay, and then after binding, it makes a conformational change. This changes the active site. This changes the conformation of the active site, and once the original key fits in, it gets jammed. Fine. So this is an example of non-competitive inhibition. Non-competitive again because there is no competition between the substrate. There is no competition between the substrate and the inhibitor. So what happens is, in this case, the original key gets locked because of the presence of non-competitive inhibitor at a site other than the active site. So how can we represent it on the graph now? I am talking about the non-competitive inhibition. So let us take an example here. So we have, this is our Reversible plot. Fine. First we start with the substrate, plotting the substrate, that is 1 by S. Then we start by plotting the the velocity, that is 1 by V0, initial velocity. And then we have a graph like a straight line that is represented in the Reversible plot. And here we have, this is minus 1 by Km. Okay, and this is your where the intersection takes place on the y-axis. It is 1 by Vmax. So let me tell you what happens in case of presence of a non-competitive inhibitor. So what happens is, you will find out in case of the non-competitive inhibition, the substrate, the affinity, that is the affinity of the active site for its substrate, it remains constant. Okay, so that's why the Km also remains constant. Now when you talk about enzyme efficiency, always what you find it as, so this is your enzyme efficiency and this is proportional to your Vmax. So how can we decipher what is happening in case of non-competitive inhibition? As I said, that the affinity of the substrate for the enzyme remains constant because there is no competition. But what happens is, because it remains constant, so the Km also remains constant. But can enzyme efficiency remain constant in the presence of an inhibitor? The answer is no. It cannot remain in the presence of the inhibitor. It cannot remain constant. It will go down. So it will go down, and so will the Vmax go down. Fine. So what is happening in case of non-competitive inhibitor? The Km is remaining constant, but Vmax is going down, and it should always go down. As I told in the beginning, Vmax never goes up. It always goes down or remains constant in case of the competitive inhibition. Okay. So this is what happens. So let us see what is happening on the graph itself. As I said, that Km is remaining constant, so we will have the same point, the starting point, but we said that the Km is decreasing. Okay, so Km is decreasing. So if it is, say, minus 2, minus 4, so nothing is happening, and this is minus 6. Okay, so nothing is happening to Km, so the graph will start from this point only. But what is happening to Vmax? It's decreasing. So when I say that this is your point number, this is your point number 2, this is point number 4, and this is point number 6. So what is happening is, normally it was, say, 2. Okay, the normal was plus 2, the value of the Vmax was 2. So because it's an inverse equation, okay, it's an inverse equation. So here you can say that 1 by 4 is, when we compare 1 by 4 with the normal one, so this is your, and this is, and so what happens here is the graph is like this. Graph is like this. So you will see that the x-axis doesn't change, but the y-axis changes. It means Vmax is decreasing. But you will ask, sir, how is 4 less than 2? Now because the equation is inverse, because of the equation is inverse, when you compare this 2 with 4, so 1 by 4 is 0.25, okay, and 1 by 2 is half, that is 0.5. So that's why what is happening is that this is decreasing. I mean the Vmax is decreasing. Fine. So now let us summarize all these and make you a simple chart where you can remember what is happening to Km and what is happening to Vmax. Again, I recall you that Vmax never decreases, so don't worry about the Vmax, but only worry about the Km. Okay, so let me recall you all the three ones, all the three inhibitions, and you can remember it forever and ever. So let us recall it very slightly. So let me tell you that if this is your Vmax, okay, this is your Km, so this case is your, this is the competitive. First we will talk about normal things, okay. So this is a normal case where there is no inhibitor, fine. Then we have a competitive inhibitor like this. Then we have uncompetitive inhibitor like this, and then we have the mixed inhibitor, or we can say non-competitive inhibitor. So let us see what happens in each case to summarize it for you. Okay, so in case of normal, we have a Vmax and we have a Km. So what is the graph looks like? The graph looks like this, the hyperbola in case of the normal, and in Hyperbolic plot it looks like this, a straight line. Fine. Now what happens in the competitive inhibitor? You will find that in competitive inhibitor the graph will look like this. This is the normal and this is the competitive inhibitor. You will find that the Km is, in this case the Km is increasing. So this is a bad news for the enzyme, because an efficient enzyme should have a very low value of Km. Fine. So now when you will plot it on the Hyperbolic plot, so this will come like this. So because Km is increasing, so because if it is a 0 and -2 and -4, so let us say the -4 is the normal one and the -2 is the lesser one. So graph looks like this. So there is no change in 1 by Vmax. So let us write it first and then tell you about the graph. So in case of competitive inhibitor, there is no change in Vmax. Why? Because when you increase the concentration, let me put the formula also here so that you can recall what is happening. Okay, so when you have formula on the next to it, it will be easier for you to decipher what's happening. The formula is, so formula is like this. It's Vmax is definitely talks about the efficiency of the enzyme, and efficiency of enzyme is inversely proportional to the Km. Sorry, let me clear it here. Let me make it better for you. Okay, so let me plot it here. This is what is happening to your Km, and let me place it like this, and now we have this is like this. Okay, so let me recall you now what is happening in each of the competitive inhibitors. What is happening to the Km and Vmax? Vmax, as I told you beginning, there is no change. So let me make it easy for you to understand. So this is your equation. This is your Vmax. Vmax always talks us about the enzyme efficiency. Enzyme efficiency is inversely proportional to your Km. and Km is itself inversely proportional to the affinity of active site for its substrate. Okay, let us see what is happening in the competitive inhibition. In competitive inhibition, affinity of an active site for its enzyme, it goes down. So it goes down. So Km increases, efficiency it increases. So because efficiency is inversely proportional to Km, the lower the Km, better is the efficient enzyme. So efficiency increases, and Vmax should also increase. But if we increase the substrate concentration, now the substrate will work and it outcompete the competitor, so it should remain constant. So Vmax remains constant. Okay, so let us say this remains constant and Km increases. This is what is happening to the graphs, that in presence of competitive inhibitor, Km increases, and the graph looks like this. This is the original one, and one with the red line is what is happening with the competitive inhibitor. So in this competitive inhibitor, Vmax remains constant and Km increases. In case of uncompetitive inhibitor, what is happening is both are decreasing. Vmax also decreases and Km also decreases. So how will you plot it on a Lineweaver-Burk plot? So this is your original, this is your 0, fine, this is your -2, this is your -4. So as I said, Km is decreasing, so its original, we will start like this, and now Km is decreasing, so -2 is decreasing, so graph is like this. So original is like this, and now graph is like this. So we have two parallel lines, so Km is also decreasing in this case. So in case of non-competitive inhibitor, the Vmax is decreasing. It always never increases. It can either remain constant or decrease. See, you can see it's always decreasing, and Km in this case remains constant, the non-competitive inhibitor. So how is the Lineweaver-Burk plot? Let us see it like this. So in this case, we are saying Vmax is decreasing, but Km is remaining constant. So if Km is remaining constant, we will have one line like this and one line like this. So this is the overall summary of the enzyme inhibitors. And if you have any questions, please do provide your comments below, and I will be there to answer your any queries you have regarding this enzyme inhibition. Please keep tuned to my channel, and please subscribe my channel so that you will get updates for the latest videos which are coming up after this. Thank you very much for your patient listening.